All right, students, let's run through the solutions here together and self-grade yourself. Give you an idea of what your score will be as we come quickly to the end of the semester, and you'll want to know this score thinking about tomorrow and the final exam. All right, so number one of the multiple choice, I printed them up here. It says an incompressible fluid is being pumped through a pipe that has a narrow region. The pressure in the narrow, let's see if I can align this a little better, in the narrow region is blank than that of the wider region. Well, that would be less than, because as we described, a pipe that's kind of wide and then narrows, or maybe for you life science people, you might describe it more as a part of the artery that is closed up. But in order to get through this narrow spot, it has to go fast in this area and slow in this area. And so in other words, it speeds up. And that was, I guess this is chapter 12. But then besides doing this continuity discussion, we also had a discussion here about Bernoulli effect. And so to go faster, it gets its energy from the pressure, so the pressure decreases. So there would be a low pressure here and a high pressure here. So it says the pressure in the narrow region is low, and then in the non-narrow region is high. And that's why narrowing or cholesterol in the arteries can lead to high blood pressure, because you have to have high pressure out here, which would be the heart, pumping the blood through this narrow region. And so you have low pressure in the narrow region, but you have high pressure in the heart, and that's where the heart has to work hard, squeezing the high pressure, and that's the medical problem with narrowing of the arteries and the high blood pressure. All right, moving on. Which of the following is not a result of the surface tension? Let's see. Must be C here. The pressure increases with the depth. That has nothing to do with the tension on the surface. All these other ones, like a glass can be filled and it can bow around because the surface tension holds it together. Liquid floats, it holds itself in spheres. That's, again, surface tension. So anyways, those are all surface tension. So the one that's not would be C. All right, actually, maybe I should put over here on the side. So A, C. No, I think it'll look better on the video if I circle it. All right, let's go on to number 3. What Fahrenheit temperature is most closely to 45 degrees Celsius? All right, well, the little formula we had was to take the temperature in Celsius, multiply it by 9/5, and add 32. So in this case, if I take the temperature of 45 and say divide it by 5, that's 9. 9 times 9 is 81. You add that to 32, and you're looking at, let's see, that would be 11 and a 3. So you're looking at 113, which is D. Okay. Two gases are kept at the same temperature. If the molecules in gas A have 4 times the mass of the molecules in B, what is the ratio of their RMS speeds of the A to B molecules? Okay, so maybe I'll go through this. It might not be so obvious, but it would be 1/2. And it would look like this. The key here is they have the same temperature. And so our definition of temperature was the average, or RMS, speed of the kinetic energy. So what you're saying is when you can compare A to B, you're saying the kinetic energy of A is the same as the kinetic energy of B. And so 1/2 times the mass of A times the velocity of A squared would have to be the same as 1/2 mass of B times velocity of B squared. And so that's really the mathematics of this statement that they are at the same temperature. Okay. Now, they're as I said, if they're at the same temperature, I'll just equate those. I'll cancel off the 1/2. And when you rearrange this and you say the ratio of mass of A to mass of B is the same as the velocity squared of B to the velocity squared of A. And so right here it says if molecule of gas A has 4 times the mass of B. So that statement mathematically is saying that A is 4 times bigger than B. So if you take that ratio, you're looking at 4. Okay, so mathematically this would look like a 4. And then this would be the velocity of B over the velocity of A squared. So then when you take the square root, you're saying the velocity of B compared to the velocity of A is a factor of 2. And of course, the other way around would be 1/2. So it could be B or C here. But then you want to go and say, what does it say? The RMS of A to that of B. So you want A on the top. So I'll take that reciprocal. So the velocity of A to the velocity of B would be taking the reciprocals 1/2. And so that's why the answer I said is C. Okay. 5. It says here 2 liters of an ideal gas is basically doubled from 300 to 600 while the pressure is maintained at 1 atmosphere. What is the final volume? Well, you might remember the PV equals to nRT. There's a lot of ways to write this. One of my favorite ways is to write it as PV over NT equals R, because R is the gas constant. So no matter what I do here to this gas, these 4 parameters will always equal to R. So I can always write the initial pressure, initial volume, initial number of molecules, and initial temperature must then equal to the final pressure, final volume, final number of molecules, and final temperature. And I find that very useful because on a lot of these we talk about how 2 parameters are related and the others don't change. Like indirectly implied in this, because of this gas, is we don't change the number of molecules. And so we're not, adding more, taking any out. We're not having a chemical reaction inside. So I'll cancel those off, and that's pretty common. But you'll also notice it says maintained at the same pressure, so initial and final. And so what you end up with is you're saying that this ratio of volume to temperature initially must be the same ratio as volume to temperature final. And so that means if one increases, the other must increase. And that's what they did. They heated it. They doubled the temperature. So from here, we doubled it. So that means our volume must also double. So this 2 liters must now become 4 liters. Okay. How many calories are required to heat 600 grams of water from 23 to 33? And we could write out the formula Q equals to MCAT if you want. But in this case, this could probably be more easily done just conceptually because the definition of a calorie was the energy needed to raise 1 gram 1 degree. So in this case, we've got 600 grams warming up 10 degrees. So we would, like I said, a calorie is each of the grams. So this would be 600 times that and then 10 times that, making the 6,000. Now here I think we got some unit conversion. A typical jogger burns up food energy at a rate of 40 kilocalories per minute. How long would it take to run off a piece of cake if it contains about 400, and there's a little subtlety here, hope you didn't miss it, capital calories. Oh, and they even helped us out. This is about 1,700 kilojoules. Let me just check that. I was thinking we were going to have to do a unit conversion because we've got 400 capital calories. And a capital calorie is 1,000 little calories. And then into joules, there is 4.186 joules in one small calorie. So grabbing my calculator here, I've got 400,000 times 4.186. And this would then be 1.67, if I do 3 significant figures, 1, 2, 3, 4, 5, 6 joules, which then, of course, would be 1,670 if I put in 1,000, and the other 1,000 goes into the kilojoules. So their unit conversion is accurate to within 2 significant figures, and I'm sure that's accurate enough to answer the multiple choice here. All right. So, like I said, we could probably save a little time and just use their conversion. Okay. So I will. Well, now I'll just use what I got and see where it takes me here. But now to get to the crutch of the problem, it says how long, and so you have the rate multiplied by time equals amount, kind of the general definition of rate, or maybe I should put rate, is amount divided by time. This is kind of the definition of what's meant by a rate, a certain amount. It could be like dollars and saying how much do you make per hour, so you're looking at your rate. So how much did you make during working a time of one day? In this case, or I was going to say it could be like fuel consumption, so many gallons per minute or gallons per second or gallons per hour, any kind of rate. Anyways, in this case, it's calories per rate. And so it looks like what we have to solve this problem is the rate, which they tell us it's 40,000 joules per minute. So there's our rate. The amount that we want to burn off is the 1,670 kilojoules. Ooh. And then let me come back to here. I'm going to put this back to kilojoules. It'd be easier because I got this side in kilojoules. Okay, so I've got 40 kilojoules per minute from the rate. And here I got the 1,670 kilojoules per, per how much time does it take? Yeah, and that's what we're after. So, kind of tight on space here. Let me move time to the other side. Then I would have 1,670, and I'll just cancel off the kilojoules. And when I bring this over, I will divide it by 40 per minute, and the compound fraction will put the minute in the numerator, and so I will take that last one, 1,670, and divide it by the 40. So we're looking at about 41.8 minutes. And I don't exactly see it, but I'm pretty sure the closest thing here is D. If I had the 1,700 and divided by 40. Yeah, so there's the 42.5 minutes. Okay, nice. All right. Oh, there's one more. I almost went to the next page. Okay, so in conduction, thermal energy is transported by, so the definition here is really these collision of molecules. And so conduction was something like this, that you had a hot object, you have a cold object. The hot ones are moving fast. They bump around, hit the slower ones. And so you don't actually have any molecules move there. There's no transfer of molecules. That would be convection. But there is a bumping and a transfer of the energy, and that's called conduction. So B would be the best answer there. All right, so let's move into number 9 here. Number 9 says, increasing which of the following would increase the period on the pendulum, the period of a mass on a spring. So looking at this chapter 16, I believe, we had the mass and the spring constants. And, of course, they're saying we want to, which of the following would increase the period? So we want this to go up. And that can go up by either the mass going up or the spring constant going down. But it says the period increasing which of the following. And so I guess it would have to be the mass there. Increasing the spring constant would lower the period. If they had decrease, we could decrease the spring constant. Okay. All right, and then finally our last one here, and again on waves and oscillations, it says if the frequency of a periodic wave is double, while the velocity remains the same. And so this is the connection between those three parameters, wavelength, frequency, and velocity. So they're saying while the velocity remains the same. So keeping this constant, and a good example of this is sound waves. If the frequency is doubled, so this number goes up by 2 times. And kind of sound waves, that would be an octave. And so if your musical note went up, and so maybe you're playing a middle C, and then you jump up to the next octave, which is a high C, or a C4 to a C5. So you've doubled the frequency, and to keep that number the same, the wavelength has to be cut in half. And so D. All right, so there's our multiple choice, and finishing up there on waves. Let's get to the free response questions. Okay, and I'll start here with the first one, and you can see it's right out of chapter 12. We've got the air flowing over a wing and an airflow. It says the airspeed over the top of the wing needs to be faster than the airspeed under the wing. This creates a pressure difference that lifts the plane. In fact, kind of reminds me of the very first one we had on the multiple choice. So we said where the pipe narrowed, it went faster. Now, this really isn't a narrowing effect, so it's not quite the same problem, but the shape and the geometry makes it flow faster, and that's for different reasons. It actually is kind of like narrowing a pipe, but the pipe, you can actually see the physical material. Let's say the pipe is made out of galvanized steel, and you can actually tell why it narrows, and see where it narrows. Whereas an airstream that narrows is narrowed because of, some kind of constraint, and obviously the wing is one constraint, but so is the air pressure, and so this is kind of harder to see a narrowing, but it is a narrowing nonetheless. All right. And that makes it go faster. And then once it goes faster, there should be a lower pressure. And so this should then be a low pressure above the wing compared to under the wing. And that's what it says. It creates a pressure difference that lifts the airplane. Most airplanes need a pressure difference of about 1,000 newtons per square meter. That's 1,000 pascals to overcome its weight. And so you might remember that force is pressure times area. And so as the engineers are building an airplane, they want to get this pressure difference together with the area that makes the total lift of the plane. And so by designing it in such a way that the pressure difference is around 1,000, then you can actually then determine how much surface area, so how big the wings need to be, combination of their width and their length, but then you can factor all those together to get enough force to equal the weight of a fully loaded plane, and of course then you have takeoff. So that's the idea, and that's what we had. So during takeoff, the plane's speed, and therefore the speed underneath, is 60 meters per second. How fast is the air above? Well, we know then if we call this the velocity on top of the wing, it has to be greater than 60. That's how we get the lower pressure, the Bernoulli effect. Okay? And then if we sit down and do the mathematics here, so 11a, We could say from Bernoulli's equation, 1/2 the density of air times the velocity squared, plus the density times g times the height of the air, plus the pressure of the air must be a constant. So that's the Bernoulli equation, which he derives from the conservation of energy. And why that's useful is because you could then have a comparison of two different places in our airflow here. And so we have, one side equaling another. In other words, we have a before and after. In this case, though, it's probably better to say this is the top. So I'll put a T underneath the velocities for this is the velocity on top of the wing. This is the height on top of the wing. This is the pressure on top of the wing. And this side of the equation, I'll put a B here for bottom. This will be the bottom of the wing. And so you can see if one were, to increase, like the velocity at the top of the wing, then one of these, we'll talk about the height, wouldn't be the height, it would be the pressure at the top would have to be lower than the bottom. And that's why I was saying the velocity at the top needs to be greater than the 60. So that number is greater, and then that one's small to make it equal. And as you probably saw in the homework and in some of the solution guides there, when you're talking about an airplane wing, there's not really a height difference between these. And oh, by the way, I guess I shouldn't have even used the word height. That would be inappropriate. That would be best labeled as depth or height within the liquid. So what I'm getting at is if you're on the tarmac and you're moving down the runway here, and that's what they are, taking off, we're measuring from the top of the atmosphere. So we've got hundreds of miles. Well, that might be a little extreme. Let's just call it 100 miles. From the top of the atmosphere down to the top of the wing, and then really the same distance to the bottom of the wing. I mean, the difference between the top and the bottom of the wing might be, 10 centimeters or something. Or maybe I'll do it in inches, depends what kind of airplane, but I said 10 centimeters. That'd be only like 4 inches. So maybe 20 centimeters or maybe 8 inches, something like that. But my point is, it is essentially the same. So as you saw us do in the solutions, when it comes to the airplane lift, we're going to say the top of the wing and the bottom of the wing are essentially the same depth in the fluid. So that's not the big factor. And we need to get rid of that. And that might be the hardest step here. I don't know. But it mirrors what we were doing on the solution. So hopefully that's not a challenging one, but you could get stuck there if you don't eliminate those. Because then the rest of this is pretty straightforward because I can then put these together. And so I'd get 1/2 times rho, and then I'd have the velocity at the top squared minus velocity at the bottom squared when I move this to the other side and factor out the 1/2 and the density, the rho. And then over here, I would have the the pressure at the bottom minus the pressure at the top. And you can move them either way, but I did want to move them so that I could put in this 1,000 because notice it says it's about 1,000. They give me this. But they also make it very clear that the bottom has a higher pressure than the top. And so depending on how you rearrange your equation, this could be a plus or a minus 1,000, depending on what order you put these in. And so if you go bottom minus top, it's a positive number because the bottom has more pressure than the top. If I had arranged it to put these on the other side of the equation, I would now have top minus bottom, and I'd have it on this side of the equation, and I'd have to put a negative 1,000. But I wanted to get a positive number here. And then likewise, I know that the velocity at the top is greater than the velocity at the bottom, and so that's a positive. So positive goes with positive, and if you set up your equation the other way around, you're going to get a negative and a negative, which will cancel off, and of course, we'll get the same answer. Let's put in our density of our air, which is about 1.2 something. Normal room temperature, it's about 1.20, so I'll use that. You can use, like, if it's a cold day, 1.25, and that's roughly sea level, so, you I guess could go a little lower if you were flying out of Denver or something like that. Anyways, but I'm just going to go with Santa Barbara here, and a regular Santa Barbara day. So I'm going to go 1.2. Then we got what we're looking for here, which is the velocity at the top squared. And then, of course, the velocity at the bottom, which actually is a fun discussion because they say go ahead and assume it's the same as the takeoff speed. And that wouldn't be quite true. You would have what we call boundary effects, and there's a whole other engineering aspect. But again, that's beyond the scope of this class. But I'm gonna take it as the problem leads, and it was written by your author, who's done a good job in this book at getting things to the appropriate learning and the appropriate level. Anyways, and now we've got a bunch of algebra to do to get the velocity at the top. So let me take this 1,000 and imagine me bringing the 2 over, so times a 2. Let me divide that then by the 1.2, and I'll just hit enter at this point. And so the velocity at the top squared minus the 60 squared would be that number. So if you can imagine moving that to the other side at this point, that would become a plus. So we'll go plus 60 squared. And so that would be the velocity at the top squared. And so my final step, and I hope you don't do this much math in your head. You should probably write it out. I have a little more experience doing the math, so I will sometimes just kind of do it picture them in my head instead of writing 3 lines. But I get 72.6 meters per second, and that's what hopefully you're looking for. Okay. So as we said at the beginning, yes, it should be going faster. All right, let's move on to what I think is the hardest one on the test. I guess you can decide. I think, the one that you kind of get confused on or stuck on is always the hardest one on here. But we've got a couple things going on here in this thermodynamics one here. And so we got a fluid flow and a thermodynamics and then an oscillation one. All right, so on this one, we have a hot sphere. So here it is. That has a surface area. And they were nice to us, giving us the surface area. Because you may or may not remember, the surface area of a sphere is 4 pi r squared. And so usually in these problems, they give you the radius and require you to figure out the area. But they were a little nicer, so okay, I'll take that as the area. And it's in a vacuum chamber. Now, this is important here because we learned that there were 3 ways to transfer heat energy: by conduction, convection, and radiation. And conduction and convection each require molecules. And so if you evacuate it, you don't have those. And you can only then transfer by radiation. That's why your those hydro flasks are so, I call them amazing, because I can put, ice water in my hydro flask in the morning, and the ice stays cold all day. Or if I just have a glass with ice in it, or a flask that, isn't a hydro flask, one that, just doesn't have the double walls and evacuated in between, it only keeps ice for a real short amount of time. Maybe an hour, maybe 2, but not all day. Anyways, and so you always, can improve the thermal insulation capabilities. Of course, I said it with cold drinks because I don't really drink hot drinks, but those thermal flasks were great also for hot drinks. You put a hot drink in there and they stay hot because they're double walled. They look, they've got a chamber where you pour your liquid in, and then you've got an evacuated chamber of it, which is why they're easy to tell which ones are evacuated, because if you just kind of tap the side of it, it goes ding, ding. In fact, not that it's needed, but I'll grab my hydro flask here. But you can just, hear that ringing and that rattle, and you can even open the top and kind of look inside. I don't know if I can angle it with the camera this close, but you can kind of see put your fingers on it and you can feel that double wall and then it's evacuated, which is the other reason, too, if nobody's told you or if you didn't read it, don't put these in the dishwasher, because the hot cycle and the drying cycle has a tendency to really cause havoc on the seals that seal that up. And then if you lose that vacuum seal, ooh, it'll just work like a regular cup now. Put that back. Anyways, so I digressed, and I apologize here. Let me get back to this. But what's important here is that they make it very clear that there is no conduction and no convection and only radiation. Okay? And that's key to the problem, because we learned that the rate at which energy is transferred has to do, we call it Stefan's law. So it's Stefan's constant. And different materials radiate better. And so this is the emissivity of it. So how well does it rate? And the best you can do is what we call black body radiation at 1. And so this is, nothing is exactly 1, but here we have 0.85. And this energy is per area, so the bigger the area, the more it radiates, and of course temperature to the 4th power. And so this is Stefan's law, and this is the rate at which energy is transferred by radiation. And so that's what we're going to do in this problem. Now, inside of this sphere, so in here we have a bunch of steam that is now condensing into a liquid. And you'll see here that what we called that latent heat of vaporization is being reintroduced as it condenses. And so as the steam condenses, it's warming the sphere. And so you might kind of think of this as inside energy is being given off, keeping it, warm in that chamber, okay, as it condenses, as the sphere loses radiation into the environment. And of course, as the little squiggles indicate, it's losing energy from the sphere. And so what is keeping it warm is this condensation. And then, of course, what's cooling it down is this radiation. But there is one more, and this is what makes it a hard problem, is that this sphere, and says the, let's see, we're going to the environment, the chamber walls have a temperature. And so this sphere would be in some kind of room, I'll just say the lab room, and the lab would be having the same Stefan effect. So for the same reason this thing is cooling itself, it's the same reason the walls radiate and shoot it at the sphere and warm it up. And so the object here, I would say, is getting warmed up because radiation from the environment is warming it, as well as the liquid, or the steam turning into a liquid, is adding energy to it, while at the same time it radiates outward. And so I guess here's what I'm getting at. Using the principle of conservation of energy, I would say, all the energies going in balance all of the energies coming out. And that's why it remains at 100 degrees. And this will continue until something changes. And in the case of steam, we know that it can't ever get less than 100 degrees until it all turns to liquid. So in this case, what's going to happen is the steam's going to be condensing and condensing and condensing and condensing, keeping this at 100 degrees until eventually all the steam is condensed. And now the water that is in there, because of the condensed steam, will now begin to cool, and it'll start dropping from 100 degrees down, and eventually it gets the same temperature as the chamber. And I suppose we could argue that it wouldn't be all the way down to 20 degrees eventually because that energy coming out then warmed the room, and so maybe the room warmed up to 21 at that point, and so thermal equilibrium is reached at maybe 21 degrees. Kind of depends on how big the room is, and depends if the room then can also be cooled or warmed and blah, 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 blah. But that's getting way past what we need to do for the problem. We just need to do this. And so I'm going to go and say, look at it as a rate, so per time. And so during this time in the process where the steam is condensing, we can say that the rate of energy going in is equal to the rate of the energy coming out. And I'll put an equal sign because, as we said, what's going in, if you will, what's keeping it warm, what's keeping it at 100 degrees is two factors. Maybe I'll even just write that here as a Q1 and a Q2, and that would be these two. The first one, I would say, would be the Stephen's law from the room, and the second one will be the condensing of the steam. And then the energy coming out is the Stephen's law that radiates it outward. So applying what we just said here about Stephen's law to what's going in, this would be Stephen's constant times emisticity times area times temperature to the fourth. And since this is going in, this would be the chamber, if you will. So I'll put a little C here for the chamber or environment, whatever you want to call it. Now, the other thing feeding energy into here, and this is one of the reasons I think it makes it a hard problem. Like I said earlier, one reason it's a hard problem is we've got both going on, the cooling and the warming by Stephen's law. But the other thing we have is we have energy coming in during this latent heat, which we said was MLV and then the time taken. And so this is the mass that is condensing, and then this ratio right here, mass per time, is really what we're looking for. This is how quickly is it condensing, and that's exactly what it says here. At what rate is steam condensing? So the mass is the steam that's condensing, and the time, the T is the time, and so we're looking for this ratio, this rate, mass per time. Now, like I said earlier, this one is also Stephen's law, but this is as it cools itself, and so this is the sphere. So I'll put a little S there for sphere. By the way, I should probably point out that this is all chapter 14 here. Is that right? Yeah, I believe 14. Okay, so hunting this down, let me do a little bit of rearranging. I'm going to bring this to the other side. So this will be Stephen's constant, emisticity, area, and it'll match this one. So when I bring it over here, I can factor those three out, and then I would have the temperature of the sphere to the fourth power minus temperature of the chamber or environment to the fourth power. So I'll get that over here. And then this, if I just kind of rearrange it, I'll put mass over time, because that's what I'm looking for, and then the latent heat of vaporization here for water. And now I can just fit in my numbers, because all of these are given, and this is my unknown. All right, so keeping in mind I want to find this, mass per time, the rate. Let's look this up. Now, this one we've done a lot with, so you might have it memorized, but it's there in Chapter 14. It's on Table 2, so it's 14.2. And let's see, what does it say there? It says it is 2,256 kilojoules per kilogram. Okay. And we'll talk about the units here, because normally we like joules and kilograms for our base unit. So I think I'm going to need to do some converting here. But I think the answer will come right here when I also look at Stephen's constant. So that's the 5.67 times 10 to the minus 8, and then there it is, joule. So I'm going to get those to match. And joule per second, so we're probably going to get a rate here of kilograms per second. And then it has a meters squared and Kelvin to the fourth. Oops, I didn't really want to put a parenthesis there quite yet because I got the emissivity of it. I don't say that well. Emissivity of it. So it's 0.85. There's the area that they mentioned earlier, 4 square meters, and that was the part that I was saying. I'm glad I didn't have to do yet one more calculation. There's a lot going on in this problem, but there's the 4 square meters. And let's see if I can fit this on this edge. But I'd have the temperature of the sphere, and I need to be careful with my units because it needs to be in Kelvin. And I know that the temperature is at 100 Celsius. So remember, you add 273 to your Celsius. So 273 plus 100 is 373 to the fourth power. Minus, and the chamber, the environment, is just kind of the room walls. Typical value of a room is about 20 degrees Celsius. But again, switching it into Kelvin, I have to go 273 plus 20, so that's 293. So 293 to the fourth power. And I guess I'll put up here Kelvin to the fourth. And so you'll even see Kelvin to the fourth cancels off, meter squared cancels off. And if I come over here and change this kilo into a little comma there, so it's 2,256,000 joules per kilogram, then this joule will cancel with that joule. And I'll end up moving the kilogram over here and matching it with what's left in the units, which is the seconds. And so there it is, kilograms per second when I have my mass per time. So now I just need to multiply these all out and divide by that number here. So, grabbing my calculator, let me do this one first. 373 raised to a power of 4 minus 293 raised to a power of 4. And maybe I'll just hit enter to get that one in my calculator. That's probably the hardest calculation. Let me just work backwards here. Times 4 times 0.85 times 5.67 times 10 to the negative 8. And that's what I get on the right-hand side of this equation. Now I just need to divide that as I bring this over by the 2,256,000. And I get a small number, 0.00102. And maybe, not needed, but if I just move the decimal 3, I'll have grams per second. So it's about 1 gram per second. So this is condensing at a rate of about 1 gram per second. So it'll stay at 100 degrees for, a while, depending on how much steam you have in there. So, maybe if we have 100 grams of steam, it's going to stay there for, 100 seconds before it all condenses, and then we have other things going on. All right. Actually, it only took a half page, but there's a lot in that one. So, like I said, hope you did well on this one. This was, I think, the harder of the group. Although, like I said before, all of them, or any one of them, can seem hard if you don't quite see the connection to it. All right, and so the last one here, looks like we're in the oscillations of chapter 16. It looks like we've got a 2,000 kilogram pickup truck, and it oscillates up and down at this 3/4 of a second. And then looks like we're going to load the pickup truck. It says how much time would be one oscillation once you load the pickup truck. And I've seen this in border crossings with not just trucks but cars, as people will. I think the border agent, shake the back of the car to get an idea of how much weight's back there. I always find that interesting, but especially in a closed trunk of a car, you can kind of shake it, and I've seen them shake a car, shake a car, shake a car. The first time I saw it, it took me off guard. I thought, what the heck's going on here? And then they did, and it's like, oh. When they got to a car that took a long time to shake, to oscillate, and then they were like, oh, you must have a lot of weight in that trunk. And then so they made him open the trunk and look inside, and I don't know if any violation occurred, but very well could have. That is where I want to go here. And so we learned here in this chapter that the period of oscillation is related to the mass and the spring constant. We did a multiple choice question like that, if you remember a few minutes back here, number 9, and had mass and the spring constant. So the first part of the problem does tell us that the period is 3/4 of a second, and the pickup is 2,000 kilograms. And that information alone will allow us to solve for the spring constant. So why don't I move the 2 pi to the other side and square it. And see what number do I get, and then we'll solve for the spring constant. So 0.75, that is first divided by 2, and then divided by pi, and then squared. All right, so this is 0.0142. And then a fairly easy step is to move the spring constant over to here, and then this number underneath. So if I go 2,000 and divide it by that last answer, I get a spring constant of about 1.40 times 10 to the 5. So there is the information I can gather from the first part of it, because the second part of this question, the main part of the question, is how much time would one oscillation be if you now loaded it with 1,000 kilograms? And that's kind of an important physical picture. That's what can make this problem a hard one, is to recognize that, okay, what do I do with that 1,000? Do I treat it alone? Do I add them? Do I subtract them? And so that's where a good physical picture comes into play here. So now that the pickup truck is loaded, I could say the period equals to 2 pi times the square root of m over k. And in this case, the total mass is 3,000. And the spring constant, I'll just put k because it's in my calculator. And then that can allow me to get the answer. But like we did on the multiple choice one back here, we said that if you increase the mass, you're going to increase the period. And so that's what's going to happen here, is now that we've increased the mass, we should get a number greater than the 3/4 of a second. So let's see what we get. So this would be 3,000 divided by, and I'll just do last answer. And so that's this 3,000 over the spring constant. Then I need the square roots of that answer. Okay, so I got that. And now I need to multiply by the 2 and a pi. And it looks like a 0.920 for 3 significant figures, seconds. And so a little bit longer. And so that's how you would roughly know how much was loaded in that pickup. Now, pickup you can probably see unless it has a cover on it, but you never know how much mass there is, especially if it's tarped and you're traveling. So you just want to, as an inspection agent, have a rough idea what's in there, see if it's worth your time, see how much weight there might be. All right, well, that's the end of the test. I hope it went well for you, and take care.